So it's our new topic. Here's our success criteria for this topic. Right, we've only got this topic and one more topic to go. Although it's quite a meaty topic. There's quite a lot of understanding and a lot of practice and skills to work on. Conservation of mass, balancing chemical equations, and writing of chemical equations to start with. Firstly, conservation of mass. What does the word conserve mean? What does the word conservation mean? To keep, right? Right? Or to keep the same. Right? So a conservative government, for example, coming up to election time, conservative government, or the Liberal National Party is a conservative government. They are ones that are about trying to save and trying to build an economy, right? So that's generally a conservative government's policy. A progressive government is one that generally spends money, right, and is more about open borders. So conservative is about closing in or holding to that which is the same, right? Progressive is changing, openness. Chemical equations are used to describe, right, it's a way of simplifying down what's going on as we observe. We can either use worded equations, right, as a simplified of a broader description of a reaction, and then we can simplify that down further using symbols. We go from reactants going to products. Really important that you're not using an equal sign. Although we call it an equation, it's not one thing plus another equals something. So it's a bit different to mathematics in that sense. Instead, we use an arrow. So very important that we use an arrow because the arrow represents moving towards or produces. So you will be marked down on your examination if you use an equals rather than an arrow. So it's something I'm rather particular about. Conservation of mass. So looking at that word conservation, it means that the total mass of a system remains constant. That's what conservation of mass means. Yeah? The total mass within a system remains the same. So if all of the reactants are used up, then the mass of the products is equal to the mass of the reactants. What usually happens, though, is that one of the reactants is in excess, so it's better to say the total mass of the system remains the same. Balancing chemical equations. You may have done some of this before, and your replacement teacher said that you had started to work on this. So we balance chemical equations by changing the coefficient, the number in front of the chemical species. We do not change the subscripts. Right? One reason for that is if we change the subscript, we actually change the substance. So the difference between, let's take the example of 2H2O versus H2O2, right? 2H2O means 2 water molecules, right? H2O2 means 1 molecule of hydrogen peroxide, right? So it's really important that we make that distinction. Because if we change the subscripts, we're changing the substance. We're not just balancing. So coefficients multiply every atom in the compound or the element. There's different ways in which we can balance chemical equations. One I like to use is called the REP method that I'll talk about, reactants, elements, products. You can think of it as a list of steps, or really it's a skill set. So the skill set is broken down into this idea. We write a word equation or a description may be already given to you. Then we write a formula for each of the reactants and products. We use numbers in front of the formula, the coefficients, to balance the numbers of atoms on each side. Check that each atom to make sure the equation is balanced by counting each side accordingly. Then lastly, we include symbols to describe the state of matter in which each of those substances are in. So S for solid, L for liquid, G for gas, and the symbol AQ to describe aqueous or a solution. I'll just pause it. Okay, one method, using integer coefficients. So this idea of two waters versus hydrogen peroxide. So talking about coefficients as to why that's important. So, REP. If we write the letter E either to the side of the equation or underneath the arrow, I find quite useful. E stands for elements, R for reactants, P for products. So if I look at the left-hand side, I have 2 hydrogen atoms, 2 oxygen atoms in total. On the product side, I have 2 hydrogen atoms, 1 oxygen atom. So what I need to do is I need to multiply the right-hand side by 2. As I do that, we can see that the amount of hydrogens double and the oxygens double. So now what I need to do is balance my reactant side by doubling the amount of hydrogens. So I put a 2 out the front of hydrogens, and that changes that to 4. So I do a check. 2 lots of 2 gives me 4, plus 2 lots of 2 gives me 4 this side. 2 lots of 2 is 4 on this side. 1 lot of 2 gives me 2. 2 lots of 1 gives me 2. Our reaction is balanced. Right, let's have a look at a few of these examples. I won't go through them all. Magnesium plus hydrochloric acid goes to give magnesium chloride plus hydrogen. So, let's do it up here. So, magnesium plus HCl goes to give MgCl2 plus H2 gas. REP. List the elements in order of which they appear. So I'm starting from the left-hand side, magnesium, hydrogen, chlorine. I have 1 magnesium, 1 hydrogen, 1 chlorine atom. On the product side, I have 1 magnesium, 2 hydrogens, and 2 chlorines. So magnesium is already balanced. Go for my hydrogen next. I've got 2 on this side. I need to double that, so I'm going to put a 2 in front of there. That doubles that, but it also doubles that, and my reaction becomes balanced. I would lastly put in states. So I'd have solid, aqueous because it's a solution, aqueous, and gas. Let's look at, say, the third example, looking at C6H12O6. So plus oxygen. Right, so this is the equation for cellular respiration, the reaction that's going on inside your body every second of every day. So you breathe in oxygen, the glucose, right, that you get from food combines with the oxygen in your tissues of your cell to produce carbon dioxide and water, and then you breathe out the carbon dioxide. REP. Carbon, hydrogen, oxygen. I don't list oxygen a second time because I've already listed it. That make sense? Yeah?
Is this PowerPoint on Canvas?
Yep, I think so. Check. If it's not, I'll make sure it's up there. So it should be under section 4. C, H, and O. Just be mindful, I've got O twice on this side, but I don't list it twice here. Left-hand side, reactants. I've got 6 carbons, 12 hydrogens. 6 plus 2 is 8 oxygens there. Right-hand side, 1 carbon, 2 hydrogens, 2 plus 1, 3 oxygens. Balance my carbons first. So you're balancing in order in which it appears. So carbon first, and then I multiply that by 6, makes that 6. But now that also affects the number of oxygens on my right-hand side. 6 times 2 is 12, plus 1 makes that 13. Okay, now I go to my hydrogens. 12 on this side, 2 on this side. I need to multiply this by 6 to bring that up to 12. 6 times 2 is 12. That balances that, but it also affects my oxygens. 6 times 2 is 12, plus 6, right, gives me 12 plus 6 is 18. Now I need to balance this side. I've got oxygen in 2 places, so I can't simply multiply this by 9. Does that make sense? So what I'm going to do, I've got 18 minus 6 gives me 12, yeah? So I'm going to multiply this by 6 to give me 12, yeah? 6 plus 6 lots of 2 is 12, gives me 18, and then that's balanced. So a trick, if we've got a polyatomic ion, remember that's an ion that has multiple atoms. If we have a polyatomic ion that's the same on both sides, treat it as if it's an element, right? And it makes balancing easier. So I've got nitrate in this example on both sides. So you can see I've got 2 lots of nitrate on this side, 1 lot of nitrate on this side. So all I'll need to do is multiply that by 2. And there we go, it's balanced. Right? It still will work if we separate each of the elements out, but that's just a neat little trick. So a couple of examples there. Half integers are particularly useful when we're looking at combustion reactions, and this is called like CHOD. Carbon, hydrogen, oxygen, double. That's what that stands for. So if I think about this example here, C2H6O2, I'm going to balance the carbons first by putting a 2 out the front here. Then I balance my hydrogens, 6 hydrogens this side, 2 this side, that would make that 3. So at the moment I would have 2 lots of 2, which is 4, plus 3 gives me 7 lots of oxygen. Balance that amount of oxygen, 7 divided by 2, or 3.5 lots of O2, right? And then we double all the coefficients together, which will give me 2, 7, 4, and 6. A few more examples I'll put up. So, and combustion reactions, that's what I was talking about. Carbon, hydrogen, balance oxygen last. It's the easiest way to consider that. Writing chemical equations are talked about. S is solid, L is liquid, G for gas, AQ is aqueous or solution thereof. Deduce worded equations from a description. Apply the symbols. There they are. So, a couple of examples. Here's a description of the reaction. When solid sodium hydroxide, NaOH, reacts with hydrochloric acid, HCl, it produces a solution of sodium chloride, NaCl, and water, H2O. So we simplify that down to a worded equation. We get sodium hydroxide, solid, plus hydrochloric acid, aqueous, arrow, sodium chloride, aqueous, plus water, liquid. And then we simplify that down further into a symbols. NaOH plus HCl goes to give NaCl plus H2O, and then we balance. Question? Yeah. Let's do one example of here. Sulfur trioxide gas can be made by burning sulfur dioxide gas in oxygen. Like a different marker. Yes, you may. Sulfur trioxide, SO3, burns in oxygen O2, gives us sulfur, sulfur trioxide can be made, so that's the product, sulfur dioxide there, right? So there's my, or I would go sulfur dioxide, gas plus oxygen gas goes to give